Goodbye.
Hello, Mr. Ryan, right?
What do you think?
Last lesson we talk about that min-max thing,
Cycle.
right? Cycle, yes. Cycle. And you mentioned what cycle?
Cycle is a thing that goes round and round, like the wheels on the bus go round and round. And also, what you said when we were little, you said we were naughty and we like poured the milk powder out of the fridge and put it on the fridge and said it'll snow.
Okay. Look, this one,
And so
cycle,
threw
yeah?
all the duvet out the window
Okay.
into the garden.
1, 2, 1, 2, 3. Okay, so in itertools, Python provides this itertools. It has a one cycle function. Okay, so what does it do? G equals cycle 1, 2, 3.
Yeah.
And then I can do this while true. While true means the indefinite loop, endless loop. And I can say print next G. Okay, so guess what happened after executing this piece of code? 3 lines of code, what happened?
It'll print 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3.
Yes, exactly. Look, G equals cycle, a parameter tuple, 1, 2, 3. And Y true means endless loop, right? Keep going. So basically, this is the BG loop, keep going, right? It never ends. Next G. Because G is an iterator. Next, move to the next, yeah? Next will be 1, next will be 2, 3. And then you go back to 1, 2, 3, okay? So without this cycle, if we change it to iterator, and this will stop after 3 iterations. Because 1, 2, 3. The next one is no elements, then you stop. We can use the second parameter, next iterator, right? This is the iterator, and then by default, for example, -1. So if we run out of elements from the iterator, if there is no such next element, we return the default. Okay, so without that, it will stop. It will stop. It will just say that it will stop. So the cycle makes it endless iterator. So in other words, cycle 1, 2, 3 is basically means this one. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Keep going, keep going, keep
1,
going.
2, 3, 1, 2, 3, 1,
Okay.
2, 3, 1, 2, 3.
Iterator makes it possible to point to an endless list. Okay, so there's no such thing as endless list. Am I right? Endless list in computer, because what's endless? What does it mean? It never stops. But you are talking about list. List is a concrete thing. It's impossible to put endless element in the computer. Am I right? If you're asking for endless list, give me an endless list. So the computer can't do it. Why is that? Because computer can't put endless element in a list. And okay, so this is endless list with all elements. Here you go. The computer can't do it, right? Okay? But with the iterator, computer can do it. Okay, computer say, okay, just imagine, I have an endless list, but I can't give you at once. Am I right? Instead, you ask me, using next, I give you 1. You ask me again, I give you 2. You ask me again, I give you 3. You ask me again, 1, 2, 3. Just imagine, this is an endless list, but I can't give you all at once. Am I right? That's the difference between list and iterator. Okay, so with iterator, you can do it this way. So with the iterator, how do I give you 1 when you ask? What's the word start with Y?
Yield.
Yield. Why? Yield means give it. Okay, so that's what it means. Okay. Okay. So how do we implement this cycle? How do we implement the cycle?
Throw it.
So usually,
Space.
I'm giving 1, 2, 3. This is not endless. This is the iterable. So you can go over it. It's limited. It's not endless. How can I turn this into an endless iterator? So let me define this cycle. Cycle x. Okay. So look, x is 1, 2, 3. Yeah? If you ask me 3 times, and I will run out of it. So after I run out of it, what happened? You ask me the 4th time, I don't have element for you. When we go through the element, we need to save copy of it, right? Saved. I have a saved, which is an empty list now. So if you ask me for it, I in x, right? This is iterator. I yield it first. I give you the element first. And then what's next? I need to put this in here, right? Saved. Dot append. Okay, so what does it mean? Look, if you yield me. If you ask me 3 times, I give you 1, 2, 3. But after that, that's fine. 1, 2, 3. I put it in saved and yield it. Right? So while saved. Why we have element in the saved? For I in saved. Yield. I. This is how we implement the cycle. This is actually very neat, beautifully written. Look, just a few lines of code defines the cycle.
It's not really beautiful.
Okay, so
It's
can you
all
tell me what are we trying to do here? Why this can work? What does this mean? Why do we need a save here? Do you understand this cycle thing? Let me write it again. G equals cycle.
I don't understand.
1, 2,
I don't understand the yield part.
Year. Okay, good question. Yeah, year. What's year? Remember what I talked about the endless thing, right? Yeah.
You give it.
Endless list. You can't ask computer for an endless list. This is concrete, tangible. Give me a list of 100 elements. The computer will fill a list with 1, 2, 3, 4 up to 100 and give it to you. Right? And the computer has memory. Yeah? The memory, the brain, RAM, memory. Computer memory is called RAM. Read access memory. Okay. So you can't put endless elements in your brain, right? You can't remember like unlimited number of elements in your brain, alright? Nobody can do that. No computer that can do that. Instead, computer can say, imagine I have an endless list. You know, it keeps growing, it never ends. But I can't give you all these elements to you at once, right? Instead, you can ask me one by one. Okay, 1, 2, 3. And you ask me again. 1, 2, 3. 1, 2, 3. Remember the cycle thing? 1, 2, 3. Okay. Yeah. 1, 2, 3. Okay. You ask me what element in the endless list iterator. Okay. 1. I give you 1. You ask me again. 2. Ask me again. 3. Ask me again. 1, 2, 3. 1, 2, 3. So when you ask it, I give it to you. Yeah. That's what it is.
You can put the list in like a circle, like 1, 2, 3, 1, 2.
The thing is endless. How do you put it in a list? As long as you stop, it's not endless. Okay, so the thing is that here is endless. It never ends.
Yeah, but apparently you're giving one number
At the time, yeah?
Yeah, and you said you can't give it all.
That's right, but I want to give you 1. Okay, so this is the one way of doing it. Yeah, look, you ask me, look, G, cycle, and then I can say for I in range 10. Give me 10 numbers in this endless list, and I can say print next G, okay? And look, it calls next G, right? Next G is an iterator, and then what it does here, yield. Once yield happens, it gives back the number to print. And then the next time you call the next, then here will continue to give the next number.
Yeah.
What have you learned today?
I think
About this,
cycle
yeah,
Cycle thing.
yield.
you're trying to return each digit in the endless list. So you have to give one element each time you ask the computer.
Because look, once I go through this X, I can't go back. For the iterator thing is that, you can't go back. So if this is an iterator, next G, and it gives the 1. Next G gives the 2. Next G gives the 3. Next G, then it will be stopping here because there's no such element after. Iterator, just one way. How do we produce an endless iterator? The trick is that the first time we go through the iterator, we save it in a copy.
And
Look, 1, 2, 3. After I finish the first 1, 2, 3, I know we have 1, 2, 3. And then the next time, we just look why we have element in the list. We just keep doing this, keep returning this. Yeah, keep returning yield. Okay, it never ends here. Right, it never ends here.
Yeah.
Why this endless thing is useful? Okay, just imagine. You know that there are unlimited number of prime numbers, right? Alright? How do we prove it's unlimited? Look, if the first prime number is P1, second prime number is P2.
A prime number needs to be an
P3.
odd number.
If there are limited number of prime numbers, let's say Pn, right? Up to Pn. And how about if we times these together?
That's limited.
Yeah.
I know. I'm proving that it's unlimited. So let's assume the opposite. It's limited and there are n prime numbers. P1, P2, P3 up to Pn. And let's times it together plus 1. Obviously, this number is not divisible by any of these, right? Am I right? So this is also a prime number. We just assume there are n prime numbers, but now we found another one. So what does it mean? The assumption is wrong. The assumption, what's the assumption? There are n prime numbers. This assumption is wrong. Okay, so what does it mean? It means we have unlimited number of prime numbers. Okay? Okay.
Wait, but you're saying P1, P2, P3, but you only have n 2 times together and plus 1.
That's right, and this
Yeah,
number
you
is a
only
prime
have-
number.
Yeah, you only have n to multiply by.
Yes.
And that's limited because you only have n.
Yes, my assumption is that, okay, let's assume there are n prime numbers.
Yeah.
And then I just found out this number plus 1 comes together plus 1 is also a prime number.
Yeah, that's only one more.
One more. Okay, so there's only one more. So it contradicts, it conflicts with the assumption there are only n. Actually, there are n plus 1. And I can keep doing this, keep adding this, keep adding this. So that means that
Wait, what do you mean keep adding?
Okay, I'm assuming there are n prime numbers, but now I found another one which is not part of this n. Okay, so I have one more number here,
Yeah,
which
but-
is a prime number.
Yeah, but how do you add another one?
This is another one. This is another one.
Yeah, so you times that another one with the other n.
Yes. So this number,
Yeah,
number
but-
is a new prime number.
Yeah, but when if you test it out, the first prime number times the second prime number, what about plus
2
1?
times 3.
Look, 2 times 3 equals 6, plus 1 equals 7. You missed a 5.
That's okay. Okay, so let's assume there are only two prime numbers, right? Let's assume, okay, we want to prove there are only two, they are limited prime number, which is 2 and 3. Now I'm telling you, 2 times 3 plus 1, this is obviously a prime number. 7.
And then 2 times 3 times 7.
Okay, so we found another prime number, which is 7. So the original assumption is wrong. They are not just two prime number, because 7 is another prime number. My original assumption is there are only n prime numbers. Now I found another one number which is prime number. So it contradicts the original assumption. So the original assumption is wrong. The opposite is correct, which is there are unlimited number of prime numbers. This is actually one beautifully proved mathematic proof
It's not
of
beautiful.
unlimited
It's not
number.
beautiful. It's not like it's colorful. It's literally black.
Neat. I'm saying neat. Neat.
Which is not beautiful.
Neat. Okay? Neat proof. Okay? Do you understand?
Yeah.
Yeah. It depends if it's neat.
Okay.
If it's
Okay, let's coming back to this prime number thing, okay? Yeah? So there are unlimited number of prime numbers. Give me the next prime number. Okay? And there are unlimited number of prime numbers. I can't give you all at once, but instead you can ask me. Okay, now I give you 2.
Yeah,
What's
yeah.
the next prime number? 3. What's the next number? 5. What's the next number? 7. What's the next number? 11.
yeah,
It's over.
but how do you get the 5? Dun.
Good, that's very good. That's actually a very, not trivial. Remember, we talked about how do we get a prime number up to 100. 1, 2, 3, 4, 5. This is numbers till 100, right? How do we get all the numbers, prime numbers up to 100? We talk about that, right? So 1 is obviously not a prime number. 2 is a prime number, right? I cross out the duplicates. 4, 6, 8, right? And then 3 is a prime number. I cross out the duplicates. 6.
They're not
Right?
duplicate, they're just in that times table.
Yeah, in that table.
Those are just multiples.
Yeah, multiple. Okay, I cross it out, right? And I can keep doing this. And the remaining are the prime numbers, right? Well, we talk about that, right? Do you still remember this one?
But how do you know if 2 is a prime number?
What's the definition of prime number?
Can't divide, it only gets divided by 1 and itself.
Okay, 1 is
Yeah. So
Start with this one.
Yeah, so you have to work it out.
Okay, so 2 is the prime number. We cross its multiples.
Yeah,
2,
but you have to work out if
4,
it's 2.
6, A, etc. And then 3 is a prime number. Cos square is
Yeah,
6.
you have to work out 2 and 3, so.
And then we walk through, okay? This is kind of the equation, okay? Do you get it now? Do you learn something new today?
But if you come from the actual prime number, you have to test if it is a prime number.
That's good, yeah. How do we test 97? Is it a prime number? How do we test it?
Well, it's obviously a prime number.
What's obvious? The computers don't know what's obvious.
33.
So how do we test it? We start with 2, and then we start with 3, and then we test the 5, 7, 9, 11 until.
No, 9's not.
Okay, until what? Until square root of 97, right? We talk about that. Eh? We just have to check all the factors up to square root of n, and if 97 cannot be divided by the factor, then it's a prime number. Okay, make sense? Yeah? Instead of checking, remember we talk about half, right? 97. Do we need to check from number 1 up to 48?
Why do you only need to check the square root?
Yeah, you are asking this question means you're thinking, yes. Look, 30. What's the factors? 2 times 15, 3 times 10, 5 times 6, 6 times 5, 10 times 3, 15 times
Where's
2.
1 times 30?
We don't check because 1 and Excel, obviously, right? Okay, and then what's next? Up to half, right? 3 times 10, 10 times 3, 5 times 6, 6 times 5. Do you see? It's in pairs. So if I have n, if I have a square root of n, the other one is square root of n. I just have to check up to half, right? The other one, 3 times 10. If it's divided by 3, it must be divided by 10, right? So I don't need to check these. These two are actually duplicate, right? So they go into the middle, which is square root of n.
But how is that square root?
Okay, how is that square root? 100.
How is that square root?
100. 100. 20 times 5. 5 times 20. 10 times 10. 10 times 10. And then the next, actually it mirrors at 10 times 10, right? Yeah, makes sense? Does it make sense now? Okay. Yeah? That's a very good question. That's a very, very good question. Means you're thinking, yeah? Okay? Okay, so that's it for today. Bye-bye.
Bye.
Bye-bye.